Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its products and experiences in mines and mineral industries. This video is confidential and may not circulate outside the receiving company without HI's authorization. Artificial hypothalamus. The power of today's technology is not in the mathematical calculations that it allows to perform, it is in the mathematical calculations that we can imagine that we can perform. The diagram presents the different links in the supply chain of minerals and their derived products. These links are mining complexes, multimodal transport system, industrial complexes, ports and maritime transport, and markets for mineral products. The table presents the models developed by HI for mining supply chain optimization. Mineral industries optimization. Cement plants advanced planning and scheduling. Challenge, to optimize the energy consumption process in cement factories. Solution, design and implementation of a mathematical optimization model to support the for planning and scheduling of the production batches, considering as main objective function the reductions of production cost and energy consumption, considering emissions constraints. Result, the model is integrated by three nonlinear submodels. Raw materials blending, kiln, and cement mill. Cement industry modeling. It corresponds to a mathematical model developed by hypothalamus artificial intelligence, to optimize operations in a cement factory, with emphasis on energy efficiency, material mixing, and emission control. The image presents a semi-detailed diagram of the cement supply chain, considering three production alternatives: semi-dry, dry and wet.
La imagen presenta un resumen del proceso de producción de cemento, desde las minas de cal hasta la producción del cemento fino.
From an energy point of view, the process can be divided into three stages. Preparation of the clinker paste. It includes the transport, crushing and grinding of the raw material, and its mixing with correctors, mainly uses electrical energy. Clinker cooking. The conversion of clinker paste into clinker is done in a linear oven and consumes heat energy and chemical energy. And fine grinding of cement, mixing clinker with additional materials, until the appropriate granularity is achieved, uses mainly electrical energy. The image shows the production of polluting emissions, which is concentrated in the clinker processing furnace. The image presents the processes of mixing materials that must be faced. Mixing processes are essential as they ensure product quality and operating conditions. The diagram shows the production line modeled in a cement factory, which can be divided into three parts, which give rise to three mathematical models: raw grinding, furnace, and cement mill. The simulation of the linear furnace must be carried out in detail, in the order of meters. This is because the chemical process that converts the clinker paste into clinker takes place throughout the kiln. For this, the temperature of the kiln must be controlled, which is generated by the chemical energy produced by the materials involved in the chemical composition of the clinker paste, together with the thermal energy from the combustion of fuels. It is used to maintain the temperature of the furnace. From the chemical process, all material streams that are produced, including pollutant emissions, can be calculated. In this way, thermal energy consumption, the composition of clinker paste, and the production of pollutants are combined. The fuel mix originates from trying to minimize fuel costs, while respecting emissions control. Given the nonlinearities and discrete nature of the integrated mathematical model, the test showed that the best alternative was to implement a math heuristic, which would speed up the solution time, and ensure a solution in the neighborhood of the optimal one. The process implemented was: a linear model of the raw grinding model is generated, which facilitates a feasible initial solution. From this solution, the problem of the kiln model is solved, which produces a feasible, quasi-optimal nonlinear solution up to this part of the process, and optimized clinker grinding on cement mill models. This solution may not be optimal, but if desired it can be improved using an iterative algorithm, which modifies the boundary conditions, based on the gradients estimated by the dual variables. The screenshot presents the GAMS program of the mathematical model, which includes the math heuristics described. The screen capture features the furnace master table, and several of the related tables in the information system. Mine systems optimization. Mine planning. Challenge: to design and implement an optimization model to decide the optimal extraction sequence of mine blocks, to meet the demand for minerals. Solution: implementation of an optimization model to mine planning. The input parameters of the model are: estimation of the quantity/quality of ore in each block, firm and/or projected demand, and sequencing rules. The decision variables provided by the model are: sequence of exploitation, extraction of blocks in each period, and estimation of the inventory at the end of each period. Result: implementation of the model in a web server to be used as MOS, mathematical modeling as a service, and use the model in proofs of concept. Mineral blending optimization. Challenge: to design and implement an optimization model for minerals blending whereas the final products are formed by combining basic minerals, and/or enriched minerals to obtain a specific quality, standardized physicochemical characteristics, within commercially and/or technical specified ranges. Each specific quality of the product is a weighted function of the percentages of each component in the mixture. Solution: implementation of an optimization model to blend minerals. The objective is the short-medium operational planning of the combination of minerals, obtained from different sources, reserves, blocks, other mines, suppliers, and others, to satisfy the restrictions on the physicochemical characteristics of the commercial and/or technical commitments at a minimum cost. Result: implementation of the model in a web server to be used as MOS, mathematical modeling as a service. Vehicles routing in mines. Challenge: to develop a routing and scheduling model for mines operations. Solution: design and implementation of a routing and scheduling model for mines operations. This includes mining areas, waste and extraction, equipment, shovels, trucks, workshops, gas stations and chemical composition, quality specification for blending. The model may consider the shotcrete application, the coating that is put to the rock once a gallery has been made in an underground mine. Result: use the mathematical model in a proof of concept for a mining company in Peru. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.